Hello, I'm Kevin Buzzard and I'm going to go through sheet 1 of the sets problem sheets in my Formalising Mathematics 2022 class. So sets behave the way you expect them to behave. These lemmas at the beginning, I'm just flagging we have A is a subset of B. This lemma says A is a subset of B if and only if for all x, x is in A implies x is in B. And of course, you might think that that's the definition of A as a subset of B, and indeed Lean thinks that's the definition as well because the proof is REFL. And REFL proofs, REFL proofs work. You prove P if and only if Q by REFL. That only works when P and Q are definitionally equal. Similarly here, X is in A union B. That's defined to mean X is in A or X is in B, and X is in A intersect B. That's defined to mean X is in A and X is in B. I've given some variant of this REFL proof. I've just written down a term mode proof without even going into tactic mode. So with those three definitions at the back of our mind, let's see if we can prove some lemmas about inclusions and unions and intersections. So the first one is we've got to prove that A is a subset of A. So if you want, we can rewrite subset def, and that will change the goal. So I should say A is a subset of A. Maybe I'm jumping ahead here. X is going to be the big kind of universe set that everything's a subset of. Maybe I should show you the variables. Here we go. X is a type, and A, B, C, and D are all subsets of X, and X, Y, and Z are all elements of X. So we've got A, a subset of X, and the claim is that A is a subset of itself. And if I rewrite subset def, you can see that we've got to prove that for all x, if x is in A, then x is in A. So how do you make progress with a for all goal? You do intro, so intro x. And now x is an arbitrary element of capital X. X is an arbitrary term of type x, if you like. And I've got to prove that x is in A implies x is in A. So of course I could just do sort of intro h and then exact h. That would work. So there we go. That has indeed worked. But sort of rather amusingly, that this is we're trying to prove that something implies itself. So we're trying to come up with a function from a type to itself, and an example of such a function would be the identity function. So I suspect exact id would work here. Yeah, it works fine. And you don't need to rewrite subset. So if I just delete that, you see the proof still works. So you don't need this. And exacted could do intro, whatever, intro h, exact h. So now what's happening here? We've got to prove transitivity of, let me increase there we go. We've got to prove transitivity of inclusion of subsets. So we could intros HAB and HBC, I suppose, intros them there. And we could keep intro. We've got to prove that A is a subset of C. So we could intro X and then HXA. So there we go. So that's the setup. We've got A as a subset of B. We've got B as a subset of C. We've got a term of type X and a proof that that term is in A. And we've got to prove that it's in C. And now remember, what does HBC say? It says blah, 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 blah implies X is in C, right? So there's some sort of implication. And the conclusion of the implication is that X is in C. We can see that, right? We do rewrite subset def at HBC. HBC actually says for all X, if X is in B, then X is in C. So it's some kind of implication with X in C as the conclusion. So with that in mind, that means we should be able to apply HBC. So I don't even need to do that rewrite there. Apply HBC. You see what's happened? The goal has changed from X is in C to X is in B. We've reduced the goal to something slightly simpler, and of course we can apply HAB as well, and now we've reduced the goal to X is in A, and so now it's exact HXA. So there's the proof of that, and of course we could just do HXA here, I would imagine, yeah. So, or apply HAB, exact HXA would work fine. Now what? A is a subset of A union B. Okay, so let's intros X and HX. So we've got the hypothesis that X is in A. And then remember, this means this goal is definitionally equal to x is in A or x is in B. And with an OR goal, we can make progress with the left or right tactic. So if we go left here, then you see we've our goal has become x is in A, which is an assumption, you know. There. So that's solved that. And now what? A intersect B is a subset of A. So we could do intro x. Oh, let's do rintro x. Because x is in A intersect B. That's the next thing we're going to intro, right? If I do intro H now, I'll get a hypothesis that x is in A intersect B. Maybe I'll just go through the trick before I pull off the trick. Let me show you the trick. And now we've got x is in A intersect B, and we've got that's mem inter if. So we could rewrite mem inter if at H. You see now that's x is in A and x is in B. And if you've done some of the earlier sheets, you'll know that the way to use a hypothesis, which is an AND goal, is we can do cases. Cases H with HXA, HXB. There. So we do an intro, and then we do a rewrite, which is definitional. So you see, we don't need to do that rewrite. There, it sort of still works anyway. And then we do a cases. And intro and cases you can do with rintro. So we could just do this straight away here. HXA, HXB. I bet that'll work. Yeah, you see, that's the same. That was the goal we had before, but I've done it in one line, and not three. And now HXB we don't even need, so I could even do that. And then this is assumption or exact, whatever you want to call it, exact HXA there. I didn't even need HXB, so we can just ignore it with a minus sign there. Now what's happening? We've got A as a subset of B and A as a subset of C, and we want to prove that A is a subset of B intersect C. Okay, so let's do intros HAB, HAC, and then we'll have an X and an HXA, I think. There we go. And now we've got to prove that X is in B intersect C. So we could do split. Then we've got two goals. You see, because I know that this goal is an AND, right? It's definitionally equal to an AND goal. It's definitionally equal to X is in B and X is in C. And AND goals you can split. If you've done the logic sheet, you'll know that you can split. So we can split, and now we've got X is in B and X is in C. And we've seen how to do these goals. So now we should do this. Pretend we're computer scientists and do it like this. X is in B. We can apply HAB there. Oh no, we can't. We can apply HAB. No, we can't, because we've got a completely crazy R, because I've got two goals named HAB. And it's applying the wrong one. Why don't we call that second one HAC? And now we can apply HAB, and it applies to the correct HAB, and we get X is in A, so they're exact HXA. What about this one? You see, we can just be lazy, right? Because you can think of HAC as a function, right? It takes a proof that X is in A, and it outputs a proof that X is in C. So we could just do exact HAC, HXA. That would work fine there. But I mean, we don't even need to do all this. We could do all of this in one go. We could just do this. We could do, what could we do? We could do exact pointy brackets underscore underscore, and then this first underscore needs to be the first proof. So that's HAB HXA, and the second one is HAC HXA. So there you go. So maybe it's sort of worth remarking. That thing there, you know, finishes the level in one move. But there's the more whatever. I'm bashing it out. I don't quite. It's very difficult to know who the audience for these lectures are now. I don't really know if people are finding this whole thing easy. I mean, let me just. I've done some of them slowly. Let me just do the rest of them quickly. So what's this one? This is Rintro's. No, this is just intro. I think intros HBA, HCA, and then X. Oh no, we can do rintros. And now this one we've got X is in B union C, so that's we could do the case. If we did the intros, we then have to do cases on that hypothesis to get the two possibilities: X is in B or X is in C. So we could do the HXB or HXC. This is an or, so we use this brackets with a slash in the middle instead of the pointies. And why is this goal true? This is exact. Exact. I mean, CC, will that do it? Oh no, rotten luck. So let's do it. It's exact. What is it? It's HBA, HXB, right? Yep, and then exact. HCA, HXC, I should think. Oh, HCA. There we go. Oops, that was exciting. That's done that one. Does Finish do these actually? No, hard luck. I'm wondering if there's just some high-powered tactic which we can use. Does Tidy do it? No. Okay. Yeah, I can't think of any more. I mean, I suppose library search might do it. Yay! There you go. Library search done that one. See if we can do library search. Excellent. You see, these statements are natural statements, and so they're in the library already. Yeah, I think that this one. I mean, this one isn't too bad, is it? This one is rintros, HAB, HCD, X, and then pointies, HXA, HXC. There, and then this is exact. HAB, HXA, HCD, HXC or something. Does that work? There we go. But yeah, the union ones are always much more of a hassle because whenever you're doing ors, you have to split into cases. So there you go. So I should say found this with library search. Right, there you go. Done them all. So that's the end of this video. Thanks for watching.